Good morning. Today, I'd like to talk a little bit about graphs of functions, both in the Calculus 1 sense of the word and in our new sense. In Calculus 1 and algebra, a function was defined to be a ruler procedure into which you can put some sort of inputs and get some sort of outputs out for answers. When we write something like f of x equal 3x plus 1, this is a description of how we do the f procedure to some number, which we are temporarily calling x here. This says take whatever number was given to you, triple it, then add 1. For example, if you did that procedure to the number -1, the result would be what we call f evaluated at -1, f at 0, f at 1, and so on and so forth. For this particular function, I can put any x into it that I feel like, and I'll get a f of x out to go with it. We usually think of plotting the inputs horizontally, and when we have the graph of a function, the actual point that we plot is the point with the same x coordinate and y coordinate equal to the function value. So when x is -1, I'm actually going to plot the point that goes with that, except the y needs to be -2. That dot is a point that's on the graph of f of x. When x is 0, the answer that I got out of this was 1. So on my graph, when x is 0, the y will be 1. And when x is 1, this x equal 1, the y coordinate on the graph will be 4. These are 3 points on the graph of the function. More generically, the graph of a function f is the graph of the equation y equals f of x, which in this particular case is y equal 3x plus 1. This would be a straight line with y-intercept 1 and slope 3. These points are particular points on that straight line. So we plot as our inputs things on the x-axis, and on the y-axis, a right angle direction, we plot things that are the function values as the y coordinates. In all of our work previously, we almost always think of y as being some quantity that's determined by x. We're going to have a different point of view now. X and y are completely independent of each other, and the point in the plane that I'm going to think about will be described by its x and y coordinates. A function is going to be a procedure that takes every point and gives me a number back for an answer. We'll symbolize this by saying f evaluated at x comma y is, for a simple example, 3x plus y. You hand me a pair of numbers, x and y, and I'll hand you back a number to go with it. The value of function f at that point. Just as with ordinary functions, I can pick various inputs, which in this case will be various x's and y's, to put into this procedure and get a variety of different answers back again. The inputs into my function are going to be all of the different x comma y's that I could think of. So I'm going to need the entire xy plane to represent the inputs into my function, meaning I can't use the y-axis to plot the function value. What we did in previous work was we took a coordinate axis that was at right angles to the inputs, and that's where we plotted our function values at. So given an xy, I'll calculate the function value that goes with it, and I'll make the z coordinate equal to the function value. For example, when x is 1 and y is 2, the function value worked out to be 5. So I'll locate the place where x is 1 and y is 2 in the xy plane, but that's not the point on my graph. I want to make the other coordinate, the z coordinate, equal to the function value. So in analogy with the single variable case, where y is equal to f of x gives me the graph of the function, for a function of two independent variables, x and y, the graph of the function is going to be the graph of the equation z equals f of x and y, which in this particular example is z equals 3x plus y. Obviously, given any pair of numbers, x and y, I can get a z to go with it. If I plotted all such things, then I would have the graph of the function. So for the function in question, the graph will be z equal 3x plus y, which if you rearrange it to say 3x plus y minus z equals 0, we recognize as the equation of a plane. So if I drew the graph of this in three-dimensional space, it's going to be a plane. I'm going to draw my pictures today using some software. I've set things up so that the color on the graph will indicate the z coordinate, as we'll see just in a moment. At first glance, this just looks like a rectangle in the xy plane with different colors on it, but this is entirely due to the perspective here. Let me change the viewing angle. You can clearly see the x-axis, the y-axis. This is the z-axis in the vertical direction. And this thing that I'm looking at is a flat plane in three-dimensional space. Here, I'm looking at it almost edge on, so you can see the flatness of it. And if I turn it about the vertical axis, you can see that it's not just a straight line or something, it's actually a plane. Purple and black mean negative z coordinates, that would be those places. Yellow means largest positive z coordinate in the picture, and in between there's red and light blue. As another example, I'm going to look at the function f of x and y equals x squared minus y squared. This is a very interesting shape. This is not a linear function, so I don't expect to get a plane or anything like that. If you look at various cross sections of this graph, this is very odd though. If I intersect this graph with all of the places where y is 0, the graph will be z equals x squared minus 0 squared, z equal x squared. That cross section will look like an upward opening parabola. If I look at the places where x is 0, that says that the function value, the z, is 0 squared minus y squared, z is negative y squared, which is a downward opening parabola. At the moment, I don't want to look at z equals 0 because of the bizarreness of it. So I'll think about intersecting this graph with cross sections in planes that are parallel to the xy plane, but are not equal to it. If z equals 1 on this graph, my graph is going to look like 1 equals x squared minus y squared, with the understanding that we are in a plane that's 1 unit above the xy plane. 1 equals x squared minus y squared has 2 x-intercepts, no y-intercepts, and is a hyperbola. On the other hand, if z is negative 1, then negative 1 is x squared minus y squared, meaning 1 is y squared minus x squared. I'll have two y coordinates that are y-intercepts, 1 and negative 1, no x-intercepts, and once again, this is a hyperbola. This is a very strange looking graph. Looked at from one way, it looks like an upward opening parabola. Look at it another way, it looks like a downward opening parabola. Looked at in a parallel plane to the xy plane above, it looks like hyperbolas that go this way. And then down below, it looks like hyperbolas that look like that. They go vertically instead of horizontally. Just like with the plane, I'm looking at this from above. Dark colors mean small function values, negative function values. That corresponds to being below the xy plane. And as you can see, I've got a hyperbola of blue color there, and the other piece there, whereas the yellowish orange goes this way and this way. This agrees with what we have figured out. Let's get a better perspective on this. Here, I can see y versus z, but not much in the way of x. It looks like a parabola that opens downwards. Here, I can see mainly the x and the z, and it looks like parabolas that open upwards. Hyperbolas down below orientated one way, hyperbolas up above orientated the other way. So this actually does look like the description that we gave. For obvious reasons, people often call this the saddle surface. Which, having had the computer-generated picture in front of me, I can draw in my feeble hand-drawn attempt at drawing that surface. One thing that we haven't really talked about yet is the idea of the domain of a function. For a given function, it may not be possible to put an arbitrary point xy in and get an answer out, or depending on your application, you may not find it desirable to let just any old point be an input. As an example of this, let's think about the function f of x and y equal 1 over x minus y. If you give me a point and ask me to evaluate this function, First, I have to figure out x minus y. There's no problem with that. Then I have to find the reciprocal of this number, and there is a problem with that one. If x minus y is 0, I can't do that. If x and y are the same number, I'm not going to get a function value back out of this. So the domain, all x, y with x and y different from each other. So I can't have any points on this dotted line that I've put in as an input. What happens if y were just a little bit bigger than x was? That would mean that x minus y would be negative and close to 0. The reciprocal will be a negative number with large absolute value. What if y was just a little bit smaller than x? Then x minus y will be positive, and the reciprocal of a positive number which is close to 0 is a big positive number. I predict I'm going to get some severely bad behavior along this straight line. On the other hand, suppose that x was much, much, much bigger than y. Then 1 over x minus y will practically be 1 over x, and 1 over a number with large absolute value is close to 0. The similar reasoning holds if the y is very large in size compared to the x. So I expect to see a picture that flattens out very quickly as I get away from this line, but acts very badly near the line. I'm looking at this sideways, and I can see that I get the kind of behavior that I was sort of expecting, but in actuality, it's worse than it looks. Nearly flat, and as we approach the line where y and x are equal to each other, on one side, my function values blow up in the positive direction, and on the other side, blow up in the negative direction. As long as you stay away from places where x equals y, it's a perfectly nice function. But at those places, it's very bad. For the function f of x and y equals 36 minus quantity x squared plus y squared, you can feed any point xy you like into that as long as the quantity underneath the radical is 0 or bigger. If 36 minus quantity x squared plus y squared were negative, you would be trying to calculate the square root of a negative number, which in our course is not allowed. So the domain is the set of all points xy that obey this inequality, which if you rearrange, that would be a disk centered at the origin radius 6, including the boundary and everything inside. Furthermore, the graph of this thing is easy enough to think about. And keep in mind that the principal square root never gives you a negative answer back. So when I write down the formula that describes the graph of the function and square it, and add x squared plus y squared to both sides, I recognize that this is the equation of a sphere of radius 6 centered at the origin, but I'm only interested in z's that are not negative. This is the top half of the sphere. Because I'm plotting stuff in rectangular coordinates, the graph gets a little jagged around the edges. So to make it look a little bit nicer, I'm only going to look at the part where x x and y goes from -4 to +4, I'm chopping off the bad grapher artifacts here. So looked at from an above perspective as usual, the point with the highest z coordinate, the yellow one, is right in the middle. Around the edges, you begin to see much smaller z coordinates, the bottom of which is 2 in this case. And looking at it from a side perspective, this is a piece of the top of the sphere that goes with x and y ranging from -4 to +4. As my last example of this introductory material, I'd like to let f of x and y be the square of something. The something is a fraction. Upstairs, x squared minus y squared. Downstairs, x squared plus y squared. You can always calculate x squared minus y squared and x squared plus y squared. The only conceivable problem you could get into would be if x squared plus y squared were 0. That only happens when x is 0 and y is 0. So this function acts perfectly nice every place except at the origin where we don't know what happens. If you didn't know any better, you would think that that's going to mean the graph is perfectly nice. It can't be anything bizarre or anything like that. Let's draw the graph of z equals that and see what we get. Once again, I'm looking at this from an above perspective, and even so, just looking at this, I can tell there's going to be some serious trouble here. Bright yellow is the biggest function value on my picture. So think of being here and getting close to the origin. There's going to be bright yellow points all the way in. I'm going to be able to get as close to the origin as I want and encounter function values that are 1, either 1 or very close to 1. On the other hand, think of being here and moving towards the origin. I don't change my color all the way in, so there are going to be points arbitrarily close to the origin where the function value is 0. But then it gets worse. There are going to be points arbitrarily close to the origin when the function value is always 0.2. I'm looking at this graph from above like we have all the other ones so that we can dramatically see just how bad this is. Let me turn this a little bit. Or maybe more than a little bit. But the moment we jump up to more than one independent variable, weird things can happen. Things like this, for instance. In an upcoming video, I'll talk some about limits and continuity, and I'll illustrate stuff with my graphing software here. This is much better than me trying to draw these things by hand. In the meantime, I hope that everybody has a good day, and I'll talk to you again soon.